Have you ever really stopped to think about how we describe the world around us? I mean, we use numbers for pretty much everything: how fast we're going, how hot it is, how much something weighs. But what happens when a single number just isn't enough? What if you need to know not just how much, but also which way? Well, it turns out there's this hidden mathematical language built for exactly that, and we're going to dive right in.
Right? Think about it. If you tell me you walked 5 kilometers, that's great. But it doesn't really tell me where you ended up. Did you go north, south? To describe a journey, or a force, or even just the wind, you need more than a simple number. You need a whole new kind of tool. And that gets us to the absolute core of this idea. See, the numbers we use every day, those are called scalars. They just have a size, a magnitude. But the moment you tack on a direction, bam, you've got a vector. So your car's speed, 100 kilometers per hour, that's a scalar. But its velocity, 100 kilometers per hour north, now that's a vector. It answers both questions, how much and which way. Okay, so if vectors are really a language, we've got to learn the basic grammar, right? Let's start building our toolkit, starting with what a vector even looks like and how we can start to play with it. So most of the time, a vector is just drawn as an arrow. And it's kind of perfect when you think about it. The length of the arrow, that's its magnitude, how big or strong it is. And of course, the way the arrow is pointing, that's its direction. It's simple, it's elegant, and it's just so powerful. Now here's where it gets really interesting, adding them together. You can't just add the numbers. Nope. You have to follow the arrows, almost like you're on a treasure map, using what we call the head-to-tail method. You start with vector A, then you take the beginning, the tail, of vector B, and stick it on the end, the head, of A. The result, your final answer, is a brand new vector that goes from your absolute starting point to your absolute final destination. And what about multiplying by just a plain old number, a scalar? Well, it does pretty much exactly what you'd guess. If you multiply a vector by 2, it just gets twice as low, but it keeps pointing the same way. Multiply it by -1, it flips 180 degrees and points in the exact opposite direction. This is how we stretch, shrink, and reverse our vectors. Super simple. Okay, so addition is like following a path. Scaling changes the length. Got it. But this is where things get really fascinating. Can you multiply two vectors together? I mean, what would that even mean? What kind of question does that even answer? The answer is a huge yes. But here's the twist. There isn't just one way to do it. There are two. Because in the world of vectors, there are two totally different questions you can ask about how they relate to each other. And each type of multiplication gives us a completely different kind of answer. All right, first up, the dot product. This is the tool you grab when you want to answer one simple question. How much do these two vectors point in the same direction? It is all about alignment. The dot product is kind of like asking one vector to cast a shadow on the other. It takes all that complicated directional info and just boils it down into a single number that tells you how much they're in sync, how much one is contributing to the other. And here is the absolute key thing to remember. The result of a dot product is not another vector. It's a scalar, just one lonely number. If that number is positive, it means the vectors are generally pointing in the same direction. If it's negative, they're pointing away from each other. Simple as that. Which brings us to the killer app of the dot product, the most important takeaway. If the dot product is 0, exactly 0, it means the vectors have 0 alignment. They are perfectly perpendicular, forming a perfect 90-degree angle. This little check is one of the most useful tricks in all of physics and engineering. It's huge. Okay, let's switch gears to the other kind of multiplication. If the dot product was all about measuring alignment, the cross product, well, it answers a totally different question. The cross product is all about creating something brand new. Now, this is a little bit mind-bending, so stick with me. Sometimes you don't care if vectors are aligned. Sometimes what you need is a direction that is perpendicular to your entire system. And the cross product does exactly that. You give it two vectors, and it spits out a third vector that is at a right angle to both of the originals. It's like if your first two vectors are lying flat on a table, their cross product is pointing straight up at the ceiling. Now, what's really wild is that the length, the magnitude of this new vector, happens to be equal to the area of the little parallelogram that the first two vectors make. And its direction? We figure that out with something called the right-hand rule. Point your fingers along the first vector, curl them towards the second, and your thumb points in the direction of the new vector. And just like with the dot product, there's a killer check. If the cross product is 0, It means there's no area between them. They must be perfectly parallel. So let's just nail this down. This slide is the whole ballgame. Two kinds of multiplication for two kinds of questions. You need to know how much two forces are working together. You use the dot product. It gives you a number. You need to find the one direction that's perpendicular to a whole spinning plane. You need the cross product. It gives you a whole new vector. So at this point, you might be thinking, okay, that's a neat math trick. But this language, it isn't just for textbooks. It is the hidden framework, the secret scaffolding behind the world you and I interact with every single day. I mean, in physics, it's everything. From the force of gravity literally pulling you down in your chair right now to the velocity of a planet whipping around the sun, you can't even begin to talk about forces without understanding direction. They're all vectors. And this goes straight into the tech you use constantly. Every single time you play a video game or you watch a movie with incredible special effects, you are looking at millions of vectors at work. They define where every object is, which way it's facing, and how light should bounce off it to make a 3D world feel real on your 2D screen. And of course, out in the real world, it's absolutely essential. Pilots use vectors to plot their course while fighting crosswinds. Engineers use them to figure out all the complex forces acting on a bridge, breaking down wind, weight, and tension into vectors just to make sure the whole thing doesn't fall down. It is the language of movement and force. So, you see, vectors aren't just arrows on a chalkboard. They are a fundamental language we invented to describe a reality that has both size and direction. Which really just leaves us with one last thought. If this is one hidden language, what other amazing systems and structures are out there quietly shaping our world, just waiting for us to find them?